Ever wonder how an AI can tell a cat from a dog, or translate languages instantly, or even write a poem? Well, it all comes down to its brain, or more specifically, its neural network architecture. So today, let's dive in and see exactly how these different AI brains are built.
So really, how does an AI think? It's not magic, it's engineering. And just like you'd need a different blueprint for a skyscraper than you would for a house, building an AI means choosing the right kind of brain for the job.
And believe it or not, the entire unbelievably complex structure of an AI brain is built from a single, surprisingly simple component. It's just like our own brains, right? Billions of neurons. AI is pretty much the same, we just start with one.
And here it is, the artificial neuron. This is the fundamental building block. It's basically a tiny little calculator that mimics a biological neuron. It takes in some information, does a quick bit of math, and then passes a signal along. Seems simple, right? But here's the thing. Connect millions or even billions of these together, and you get some truly incredible complexity.
Every single one of these neurons has a four-step job. First, it listens. It gathers inputs from other neurons. Second, it weighs those inputs, deciding how important each piece of information is. It's kind of like prioritizing its to-do list. Third, it adds everything up and makes a decision. Is this signal strong enough to pass on? This is the firing moment. And finally, if it fires, it sends its own signal out to the next layer of neurons.
So you might be wondering, what's the simplest brain we can build with these things? Well, that would be the feed-forward neural network. You can think of it as the original blueprint, the OG. It's the starting point for almost everything that came after.
The key idea here is just how straightforward it is. Information flows in just one direction, like a river, from input through some processing layers to the output. And crucially, it has absolutely no memory. It only knows what it's seeing right now. It has no concept of what came before.
And that, right there, is the big problem. This basic brain is blind to spatial patterns. It can't tell how pixels in an image are actually arranged. And it's totally forgetful. It has no idea about order or time. To solve these pretty major problems, we had to get creative and design more specialized brains.
So, to give AI the power of sight, engineers came up with our very first specialist, the convolutional neural network, or CNN for short. And you can pretty much think of these as the eyes of the AI world. Now, the secret sauce of a CNN is something called a convolution. Just imagine a tiny little spotlight, or a filter, that scans across an entire image. This spotlight is trained to look for one specific thing, like a sharp edge, or a curve, or maybe the texture of fur. Then, by using hundreds of these little feature-detecting spotlights all at once, the network can build this really rich, layered understanding of what it's looking at.
And the evolution of these networks, it was just incredibly fast. It really started back in '98 with a model called LeNet-5, which was used for recognizing handwritten zip codes. But the real explosion happened in 2012 when a model named AlexNet just completely destroyed the competition in a huge image recognition contest. That moment kicked off the modern AI boom. Just a few years later, in 2015, ResNet came along and allowed us to build these unbelievably deep networks, which led to the powerful vision systems we all use today.
And I guarantee you use these every single day. When your phone automatically tags your friends in photos, that's a CNN. When a self-driving car spots a pedestrian or a stop sign, that's a CNN. And they're also totally revolutionizing medicine by analyzing medical scans to help doctors diagnose diseases way earlier and more accurately.
Okay, so we've given AI sight. Awesome. But what about memory? For tasks that involve sequences, like language or time, we need a totally different kind of brain, the recurrent neural network, or RNN.
The real magic trick of an RNN is its loop. As it processes a sequence, let's say word by word in a sentence, it keeps this little bit of context called a hidden state. This is basically its short-term memory. The information from the first word gets passed along to help it understand the second word, which then gets passed to the third, and so on and so on.
But there's always a catch, isn't there? This memory, it's really short-term. For a basic RNN, by the time it gets to the end of a long paragraph, it has pretty much forgotten everything that was said at the beginning. It's a famous issue called the vanishing gradient problem, and it was a huge limitation for a long time.
The solution was this really ingenious upgrade called the Long Short-Term Memory Network, or LSTM. Think of it as an RNN, but with a way better memory system. It has these special mechanisms called gates that act like little bouncers, carefully controlling what information to keep, what to forget, and what new stuff to add to its long-term memory.
And this ability to remember sequences powers some of the tech we rely on the most. Your phone's autocomplete that guesses the next word? That's an RNN. When you talk to Siri or Alexa, an RNN is processing your speech. Heck, they're even used in finance to try and predict where stock prices might go next. But even these supercharged LSTMs had their limits. Then in 2017, a new architecture was introduced that didn't just improve on the past, it completely changed the entire game. This was the birth of the transformer.
So what was the big problem with RNNs? Well, they had this fundamental bottleneck. They had to process everything one word at a time. This not only makes them slow, but it means you can't really speed them up with modern hardware like GPUs. Transformers just shattered that limitation. They look at every single word in a sentence at the exact same time. This was the game changer that let us train them in parallel, dramatically cutting down the time and unlocking the ability to build the absolutely enormous models we have today.
All of this is made possible by a brilliant mechanism called self-attention. What it means is that for every single word it's looking at, the transformer can also look at all the other words in the sentence to figure out the full context. It learns which other words are the most important for understanding that one specific word. This gives it a much deeper and more nuanced grasp of language.
And this one big idea spawned a whole family of incredibly powerful models. You've got models like BERT, which are designed to understand language deeply, and then you have models like GPT, which are designed to generate human-like text. They've even adapted the whole architecture for vision, creating models that can literally see using attention, which is just wild. But what's truly staggering about transformers is how they scale. This chart shows the dramatic jump in size from GPT-1 to GPT-3, and it's just massive. Researchers found that with this architecture, making the model bigger and feeding it more data doesn't just give you small improvements, it leads to exponential gains and unlocks entirely new capabilities that the smaller models simply didn't have.
So, let's just quickly recap our AI toolkit. If your problem is about seeing spatial patterns, like in a photo, you're going to reach for a CNN. If it's about remembering things in a sequence over time, you use an RNN, or its more powerful cousin, the LSTM. And if your task is to understand really deep context and complex relationships, well, the transformer is your absolute state-of-the-art tool.
And that really brings us to the core takeaway here. There is no single best AI brain. The real art and science of AI development is all about understanding the problem you're trying to solve and then picking the right architecture for that specific job. There's no one-size-fits-all solution.
Which leaves us with a pretty fascinating final question to think about. We've built these incredible architectures for seeing, for remembering, and for understanding context. But what are the next great challenges? What new problems are out there that will force us to invent entirely new kinds of AI brains?